University. Edith is a PhD student of Thorsten Jokins and Cornell, and he works on counterfactual machine learning and mostly machine learning for interactive problems, as he can describe in more detail soon. Edith has a two-term intern, right? Two-term with Microsoft Research, or three? Three terms.
All my internships.
I see, all the internships. So he seems to really like Microsoft Research. And then today he's going to talk about counterfactual evaluation and learning for machine learning and interactive systems. And without further ado, let's start the talk.
Thanks. Good morning. Thank you all for coming. First of all, thanks Li Hong for the introduction and for inviting me over, hosting me. It's always great to be back in Building 99. So I'm Adit. I'm a PhD student at Cornell, advised by Thorsten Jokins. I study machine learning for interactive systems, and in particular, how we can reuse the data that we collect from these systems to help evaluate and train these systems in a principled manner. But for the deep learning team, for this audience, I want to get across one key message, right? When training deep learning models, pay attention to the confounding biases that could go into the training data. And I want to impress upon you that it's quite easy to train these deep learning models directly with logged user behavior data rather than just supervised data once you start paying attention to these confounding factors. So I'll talk about advances in off-policy evaluation and learning techniques. These are quite orthogonal, and as you'll see through the talk, they are very compatible with deep learning. So it's a natural fit to each other. So this is going to be an interactive talk, so please stop me at any point of time and ask questions. I also wanted to call out attention to a tutorial that Thorsten and I gave at SIGIR in July that goes into much more detail and gives a more comprehensive overview of the current state of the art for evaluation and learning using counterfactual techniques. So let's begin. Interactive systems. By that, I mean systems that interact with and learn from user behavior. So these are ubiquitous today. Think digital services like search, recommendation, e-commerce, entertainment services, but they are going to be increasingly ubiquitous with the cyber-physical systems of the future. Think self-driving cars, smart homes, and so on. So we collect petabytes of user interaction data from these systems, and we use them to help personalize these services to our users, or to help evaluate the utility that these services bring to our users, or we try to improve the machine learning models that are key components in these services. Things like learning to rank algorithms or collaborative filtering algorithms for recommendation, ad placement algorithms, and so on. So I study how we can train learning to rank, collaborative filtering, and these other machine learning models in these interactive systems. So these systems have a characteristic interaction loop, and I'll illustrate that via a toy example throughout the talk. So think about a user, say Alice, who arrives at our service and issues a command. I'll call that a context throughout the talk, and I'll denote that by X. The system responds with an action. I'll call that Y throughout the talk, a prediction or an action or an intervention. And then we get to see how the user reacts to the action. So throughout, I'll call the feedback that we collect about user behavior delta. You can think about delta as encoding the quality of the action taken by the system.
More like a reward function.
It's a way to think about reward function. But you can think about like the way we do interactive systems today. You might think about revenue or click-through rates or the things that you would typically measure in online A/B tests. These are naturally numbers, and you can think about those as encoding some function of the quality of taking this action, right? So when I say we have collected petabytes of data, I want you to think about these X, Y, delta triplets, okay? And in this news recommendation scenario, what's happened is Alice asked for tech news, we recommended an article, and we then got to see that, hey, she liked it pretty well, right, for example. To illustrate that this sort of characteristic interaction loop happens a lot, think about ad placement, right? You are on a landing page. We now need to decide what ad to put in the slot. So you can think about the context as the user and the page that you're on, the action being what ad you actually show, and the reward being did you click it or not, right?
So analogous to supervised learning, you can think of it as the same problem as Y from X to Y, except for supervised learning, that feedback is increased object function, otherwise drop So this is now
Exactly, 100%, right? And we'll exactly make that precise. The bandit feedback nature of this problem, we'll make it precise in a couple of slides. So just to illustrate that this kind of characteristic interaction loop happens in a whole bunch of interactive services, think about news recommendation, right? That also has this XY delta interaction loop. You can think about the context as being the user who shows up at the service, Y being the portfolio of articles you recommend, and the feedback being, well, how engaged was the user, right? How long did they spend reading the recommendations? Search can be thought of as this interaction loop. Users issue queries. We take an action, which is to show a ranking. And then we can see, for example, are we doing better than just some baseline ranker via some online interleaving experiments? So the goal here is to take these XY delta triplets that we collect, right? Like these petabytes of logs that we collect, and help use that to evaluate and train our models. So I'll provocatively argue that the way we are building interactive systems today don't achieve this goal, and so I call them non-solutions. So the way we typically do this is take some off-the-shelf machine learning algorithms and do something offline, and then flight them in online A/B tests to see if we actually make an improvement in our key performance metrics, KPIs. On the one hand, like online A/B tests are a very powerful tool, but you can think about them as just ignoring these petabytes of logs. Every new candidate you come up with, you have to flight it in an A/B test. You have to see how you have to let it actually make actions to the user population and see how it's doing. And in some sense, could we not do an offline A/B? Could we not go back to these petabytes of logs and use that to inform our estimates for how good a system might be doing, even before we actually deploy it in an A/B test? You can also think about bandit algorithms, which very cleverly trade off exploration versus exploitation in these partial information settings. But again, could we not warm start our bandit algorithms by already reusing a whole bunch of log data that we have access to? You can also think about the offline machine learning that we do, right? The supervised machine learning algorithms as taking a more expressive kind of data. So if you could take the logs and you could annotate them with what's the correct action to do. And if you were to give a loss function that tells you, well, if you didn't do that, how badly are you off? Then we can do very powerful supervised machine learning, things like cross-validation to pick good models, things like deep learning to actually train very powerful function approximators, and so on.
In that part, there is still the problem of missing exploration because you just can never get exponentially large number of.
Exactly, right? So that is still. So this, like if you're just going to take your observed data and annotate it, you're still susceptible to this issue of was this data representative enough to begin with, right? But you can think about these counterfactual evaluation techniques as a way to do offline A/B or a way to do warm start bandit algorithms. You can also think of it as a way to take very powerful supervised algorithms or very powerful model selection techniques and have them apply not just to this data, but directly to log data, okay? A personal rant that I like to make here is I shudder to think of personalizing self-driving cars the way we personalize ad placement today, right? I shudder to think of doing something offline with no guarantees, running an online A/B flight, counting the number of crashes, and then like rolling back a self-driving car policy. So these counterfactual techniques are going to become more important, and we would need more reliable guarantees. And the fact that we have collected petabytes of logs is a good way to begin reusing those logs to do this. So again, to re-emphasize, I want to reuse the logs. I don't want to ignore them. I don't want to annotate them. I want to reuse them as is to help evaluate and train these models offline. And the key challenge, as Lee alluded to, is we don't get full information. So in this toy example, supposing we had a new system and we wanted to evaluate how good this new system is doing, and the new system is recommending Chromebook. As we replay the logs, as we try to reuse it, we find that the new system recommends a Chromebook article that we haven't seen in the logs. We have never seen how users like Alice respond to articles like Chromebook. What would Alice do? Right? This is an example of a counterfactual question I don't have a good answer to. Okay? But this is also the key point of bandit feedback. You get to see feedback for the actions you took, but not for all the other possible actions you could have taken, which is what sets it apart from supervised learning. So luckily, there are two counterfactual questions that keep coming up when we try to design these interactive systems, and we have made some good progress in answering them. So there is the evaluation question, which is how good is a new system? right? And I want a way to do something like an offline A/B. Like I don't want to rely only on an online A/B test to understand how good a new system is. I want to reuse the logs to inform those estimates. And the second is the learning question, which is I have a machine learning model. It has a bunch of parameters. Help me find the best parameter settings. Okay. So I'll be talking about two projects, one addressing each of these questions. The first is the MNAR project, and the one-line summary is I want to evaluate and train recommender systems directly using user-generated movie ratings. And I want to do that using a new approach that relies on causal inference. So I want you to think of movie recommendation. So you have a population of users, you have an inventory of items, and the goal is to recommend movies to users that they would like, that they would derive a lot of utility from. So you can think about a subpopulation of users who like horror movies and a subpopulation of users who like romance movies, and three genres: horror, romance, and drama movies. So the numbers here, you can think of this as the utility that they derive if you recommend this movie to them. You can also just think of these as the star ratings that the user gives after they have seen the movie, like how much did they like it. Okay? So I've given you this sort of full matrix of user preferences, like horror movies, romance lovers like romance movies, and so on, right? The trouble, of course, is we never get to see this full matrix of user preferences. We only get to see a tiny subset of observed user movie ratings, okay? And what's worse, users are more likely to rate the movies that they like. So in this data set, the 5-star ratings are overrepresented compared to the 1-star ratings. So this tells you that you aren't seeing a uniform random subset of the preference matrix. The missing ratings have gone missing, not at random. So, and then Marlin and Zemel were the first to actually give the name MNAR. And I gave an example of a user-induced bias that causes this missing not at random problem, but it's not just user-induced. You can think about system-induced selection effects too. Imagine Netflix was running a promotion campaign to heavily promote House of Cards. So every user who lands on the Netflix homepage sees an ad for House of Cards. As a consequence, there are a lot more views of House of Cards, and as a consequence, more observed ratings for House of Cards, right? So you could have user-induced or system-induced selection biases that go into the set of observed ratings that you actually get to see, and that causes the data to go missing, not at random. The question is, what could possibly go wrong if we just ignore these biases? So this is not a straw man question that I'm raising just to knock it down a second later. Much of collaborative filtering research ignored these selection bias effects. So let's think about trying to evaluate how good a recommendation policy is, okay? So this was the true preference matrix in that toy example. Now imagine I have a recommendation policy that recommends 2 movies for every user. So every row here is a user, and the 2 squares that I draw are the 2 movies that are being recommended to each user, okay? So just at a glance, if I look at it, most of these squares are 1-star movies. They are basically recommending pretty crummy movies to the user population at large. But remember, we never have access to this full preference matrix. We only get to see a holdout set of observed user ratings. And remember that holdout set of observed ratings had 5 stars overrepresented and the 1 stars underrepresented. On this holdout set, if you ignore these biases, you conclude that, hey, this is not a bad policy. Most of the squares that you have a color for are 5 stars. Not too bad, right? The policy is not good. It's the data set that is biased and has given us a wrong conclusion, right? You can also think about the Netflix challenge, right? There was $1 million prize money on offer. The challenge was to come up with a way to take some set of observed ratings and complete the entire preference matrix. So you have to predict what's the rating that a user would give for any item, right? Now imagine we come up with one way to complete the matrix, which completely ignores this diagonal structure and just recommends 5 stars for everything, right? And imagine instead we had another way to complete the matrix that figures out this diagonal structure, that there are romance lovers who like romance movies and horror lovers who like horror movies, but then it makes a mistake on the drama movies. It overestimates what rating a user would give for the drama movies, right? On the full preference matrix, it's immediate to see that this way of completing the matrix, the one that gets the diagonal structure, is a better one than the other one. So mathematically, this is predicting a 5 star for 3 stars. That is predicting 5 stars for 1 stars. So this is probably a better thing to do. But remember again, we never have the full preference matrix. We only get to see a set of observed ratings that Netflix held out, right, from the competition. On the set of observed ratings, this one doesn't seem to make as big an error as this other one, right? But that's because the 1-star ratings are underrepresented in the set of held out ratings, not because the way we completed this matrix was inherently better. So train test splits are not the right way to address these selection biases, because both the train and the test distribution, when you just do a holdout, are coming from the same selection bias distribution. So in this project, we connected the recommendation problem to the potential outcomes framework in causal inference. So in the classic causal inference setup, you have a set of patients, you have an inventory of treatments, and you assign patients to treatments. Okay? Every possible assignment you could have made could have generated an outcome, and so you have a universe of possible outcomes. Of course, you can't assign a patient to every possible treatment, you can only assign them to some, and so you only get to see the outcome for the assignments that you actually did. Right? So you can think of a one-to-one correspondence between users and patients, items and treatments, the full preference matrix as your counterfactual outcomes, and the ones that you get to see, the observed ratings, as the factual outcomes. Right? Now, the key concept in causal inference to derive unbiased estimates for treatment effects is to think about how you assigned your patients to treatments. If you understand the assignment mechanism, then you can draw reliable causal inferences. So let's try to do that. Let's try to understand the assignment mechanism that could be going on in this recommendation scenario, because remember, we weren't in control of what users rated what movies, right? Users could go through and rate whatever movies they felt like. So can we still understand what's the assignment mechanism that underlies this recommendation, the data that we actually get to see in this recommendation setting? So luckily for our problems, this assignment mechanism, understanding this assignment mechanism boils down to knowing the marginal probabilities for seeing a particular user item rating. So that's what I'm denoting here by PUI, the propensity. So it's the probability that a user U would rate an item I, right? Now, if we knew these propensities, and if we had unconfoundedness, which is to say that the outcome of a treatment is independent of assigning a patient to the treatment, right, conditioned on these propensities, then we know that this inverse propensity scoring estimator is an unbiased estimate of a treatment effect. So I've just instantiated it for the Netflix challenge example. So imagine we were trying to reconstruct user preference matrices. It's looking very similar to the way Netflix actually did it, right? You go over your entire holdout set and you look at how good you are at reconstructing, how good you are at predicting each of those observed ratings, but then you reweight it by the probability of seeing that observed rating. Okay? So on the right, I'm showing you the matrix of propensities that I used to generate that horror lovers and romance lovers example. If I had just used these propensities when evaluating my policies or when running that matrix completion challenge, all the problems that I talked about earlier would have gone away. So this IPS estimator has been used in a whole bunch of fields, things like off-policy reinforcement learning, domain adaptation, contextual bandits, and it extends to things, anything that can be written as an average treatment effect. So it's not just specific to reconstruction error, right? So yeah, the key point here becomes this propensity matrix. How do I get this propensity matrix? It feels like I've taken one problem and replaced it with another, right? So there are two possible scenarios or two possible avenues to get this propensity matrix, this marginal probability for seeing a user item rating. In classic causal inference, when you are designing experimental studies, it's a controlled setup. So we are assigning patients to treatments. In those scenarios, when we control the assignment mechanism, we can simply log the propensities for assigning patients to treatments. Okay? So this is quite a natural fit for things like ad placement, where we control what ads get shown to users, and we are simply checking whether they click on something or not. Okay? But in observational studies, which is much closer to the recommendation problem that I just laid out, the assignment mechanism is not under our control, right? So users are completely free to go through the inventory and browse it any which way they want and give ratings. In this scenario, we need to estimate these propensities. And causal inference basically tells us that we try to record features, covariates about our patients some covariates about the treatments, and we are now we are guaranteed unbiasedness only if the outcome was independent of the assignment conditioned on these covariates, right? So estimating propensities allows you to say things like, hey, if I record some demographic information about my users, let's say they are male, female, etc., right? And if I record genre information about my movies, then by estimating propensities, I might discover that males tend to like certain genres of movies more, tend to be more promiscuous in giving me ratings for certain genres of movies compared to women, okay? And that allows me to reweight these selection effects when I start doing population level aggregates for my rating prediction quality, for example. A little bit more about estimating propensities. So you can think about trying to estimate P as just a supervised regression problem, because all I'm after is trying to estimate the probability of a binary random variable. Will I observe this rating or will I not observe this rating? And you can think about the targets for this regression problem as a completely known quantity. In my preference matrix, if I saw a rating, that's a 1. If I did not see a rating, that's a 0. So you can think about recording user covariates for all the users and some item covariates for all the items, and just using something like logistic regression to try to predict what's the probability of seeing a 1 or a 0 here based on those covariates. You can also use things like naive Bayes, like I know what the rating actually was. So conditioned on that rating, I can make some independence assumption and just estimate the probability of seeing that rating. I can think about, again, doing a low rank approximation of this binary matrix using a Bernoulli matrix factorization and so on. So we have a wide array of standard supervised regression algorithms that we can throw at this problem, right? But it's
so this regression of the input-output, can you say that again? The input would be...
So the inputs could be things about the user, things about the item, the rating that they actually happen to show, because...
All the input, you put them in the vector.
Yeah,
and
right?
The output will be...
Was that rating observed or not observed, right? And now throw it into a regression problem that's able to give me numbers between 0 and 1, right? So things like logistic regression or naive Bayes or Bernoulli matrix factorization and so on, okay? The thing that we found in both theory and in a whole bunch of semi-synthetic experiments we did is that this IPS estimator actually tends to be very robust to inaccurate propensities. So remember, we don't actually need to get these propensities exactly right. All we need to do is get it better than uniform random, because uniform random is as though we are ignoring these biases. And so I don't want to argue that we are doing something amazingly good. I'm just saying that we are beating a very easy baseline to beat, okay? The other thing to note is this introduces a new way to play a bias variance trade-off. Remember, these inverse propensities are going in the denominator of whatever metric we care about. There is opportunity to overestimate some small propensities rather than underestimate them, because underestimation errors in a denominator actually causes catastrophic errors, right? So you can start playing these additional bias variance games and thinking about ways to tolerate errors in the propensity estimation step, because although it introduces bias, it will reduce the variance of any subsequent machine learning that we want to do, okay? So it naturally segues into what we actually want to do, which is just drop it in as an addition to collaborative filtering. The way we used to do collaborative filtering like a decade ago was via simple matrix factorization. So I've just written out the traditional matrix factorization objective. You just go through all your training data sets and look at how well your low rank approximation recovers the ratings that you actually got to see. The only change here is we have introduced this additional propensity weighting. So you can think of this two-step process. One, use supervised regression to get propensity estimates, and then throw it into a weighted matrix factorization algorithm, right? I do want to note that we have done a lot of research into weighted matrix factorization, and people have come up with heuristic ways to weight the objective. What this causal inference technique does is it gives you a principled way to set those weights. It allows you to reason about what you need to record to do unbiased inferences, what's the bias variance trade-off that you can play, and so on. I also want to say that this is a first discriminative approach at the MNAR problem. Ever since Marlin and Zemel first approached this as this missing not at random problem, there have been a series of generative models that tackled it, right? And these generative models try to say, well, what's the process by which users rate movies? What's the process by which these ratings go missing, right? And tie them all with latent variables that are governed by the users and the movies, and then do some pretty sophisticated approximate inference like expectation propagation and so on to derive unbiased estimates for what's the rating users could give for different movies. So
I'm not familiar with that part of literature, but as the upshot, are they equivalent at the end mathematically?
No, they're not. And empirically, the jury is out. Next slide, we'll see how they perform empirically, right? But on a theoretical level, you can think of this as a generative model where we said, here are a bunch of latent variables, and now I'm defining a joint probability over everything. All the ratings that I observed, all the ratings that went missing, right? And I'm now trying to draw, well, what are the unbiased parameters in this model will actually correspond to the unbiased rating that a user would give for every possible movie.
So now the problem with that generative approach, I mean, that's exactly the same thing as in speech, right? We used to do generative. The problem is that when you learn the parameters, you don't take into account end to end. So the goal you won't have.
Exactly.
Right?
So
that's the problem, right?
Right. So the thing.
As good as that one.
So discriminative approaches directly try to minimize the risk of making certain predictions, right? And they're directly optimizing for this. You can think of generative models as trying to minimize the negative log likelihood of all observations, right?
So
under
you
a
need to
joint.
combine them. In our community, people combine them in a different. You can take the best of both.
So in what you'll see, what we'll end up doing is we'll be using a simple discriminative algorithm like this. The propensity estimation is completely open, right? You can think about using generative models as a way to get calibrated propensities too, right? Over here, we just use logistic regression and naive. Like naive Bayes is the most trivial generative model you could come up with for seeing probabilities of some rating going missing. So the good thing about this is by decoupling these two, there are no latent variables going on. I only need to know the propensities of observed things. I never need to start estimating what's the latent variable for some other user item rating.
So then how does this concept of bandit, exploration come into here? That's
So
not there yet.
No, we are not there at all. So in both the projects I'll be talking about today, the data that I've already got access to is a form of logged exploration. So I'm not talking about an adaptive explore-exploit algorithm that's now figuring out how to explore, right?
Yeah.
Over here, the users went through my inventory in some very complicated way and gave me ratings for movies. Access to that rating is as though I've got some logged exploration data. It's just that I have no idea what scheme they used to explore the inventory, right? And what processes drove them to give me the ratings that I actually got to see, right? So you can think of all I'm talking about today is how do I exploit given access to logged exploration.
Okay.
So I also want to call out that here is a natural way to drop in neural collaborative filtering, right? You don't need to do low rank matrix factorization this way. Take your standard neural collaborative filtering algorithm like deep neural nets. They also try to minimize the reconstruction error plus some regularizers and optimize it via stochastic gradient. We are also optimizing all of this via stochastic gradient and back propagating losses. The only thing you have to do is reweight losses with inverse propensities, right?
So you're saying this part can be replaced by deep neural net.
So this part can be replaced by a deep net. Nothing changes, and it plays well with each other, right? You're completely free to, and then just like that, you can also throw in, rather than Bernoulli matrix factorization, softmax layered propensity estimation too, right? So the thing is, this is a first step at doing a discriminative approach to the missing not at random problem. Yep.
You're starting. Are you accounting in any way for, say, the propensity? There's a propensity to watch the movie, which is probably heterogeneous across the different types of movies. And then, given that you watch a movie, there's a different propensity to rate the movie. Are you sort of decoupling these, or is this right now we're treating it as one? So not dealing with those kinds of interactions.
So we could. So that's exactly what I meant by we could have more elaborate models to estimate these propensities. Over here, we use naive Bayes and logistic regression. So the reasoning behind this was, hey, I need to be better than uniform random, right? And I have some deep suspicions about how good these generative models could actually be. How well can you actually do this inference across a whole bunch of latent variables? So let's try something really simple and see how good it does, right?
Makes sense.
And then, but I completely, that's a natural way to sort of scaffold and get better propensity estimates too. Future work. But on an empirical data set, let's look at how these things behave, right? So we looked at two real-world data sets. And these data sets are special in that there was a held-out test set of ratings, which was completely uniformly at random. So Marlin and Zemel invited a whole bunch of the users who took part in the study back to the lab and had them rate uniformly randomly chosen songs. Okay, so yes, you had a training data set which could be arbitrarily selection biased, right? But then you had this holdout test set where things were uniformly at random missing. Similarly, we did the same thing with Mechanical Turkers who were going around trying to buy quotes. And then, like, Marlin and Zemel did not record any covariates about users and items, and so we were forced to use very naive things like naive Bayes to estimate propensities. Over here, we recorded some covariates, so we could also try out like logistic regression as a way to do propensity estimation, right? And so we are doing whatever training algorithm we want on the MNAR training set, but we are reporting the reconstruction error on the test set. So we are essentially redoing the Netflix challenge. That's the numbers I'm reporting here. We also tried out evaluating the quality of a recommendation policy and so on in experiments in the paper, right? So mean absolute error, mean squared error, lower is better. The IPS is the one where we do this propensity-weighted collaborative filtering, and the naive is the one which is not doing that, but it's still a discriminative model that's directly trying to minimize exactly that quantity. So it's trying to minimize the mean square error. These two are two generative models from 2014, like the state of the art for doing missing not at random, with different sort of priors on the latent parameters, right? So the key takeaway is this discriminative approach gives you a very tractable, simple way to get pretty competitive performance on different data sets.
And the numbers you're reporting are the propensity weighted numbers or the raw?
The test set had no uniform, had no biases, right? It was uniform random, so there are no propensity estimates there. But that's a very good question, right? Because the reason why we wanted to have this holdout test set with uniform missing at random is because otherwise there is this chicken and egg problem, right? You can knock down, hey, your propensity estimates are wrong, so if you start reporting propensity estimated numbers on your test set, that's bogus, right? Like you can't compare apples to apples. But that's the reason why we look at these held out missing at random data sets.
So how did you choose the regularization parameter?
Cross-validation, right? So discriminative models. I have my training. So I'm doing propensity weight. So if I'm taking this approach, I'm taking my training data set, I'm splitting it, I'm doing 4-fold cross-validation. Whatever propensity estimates I'm getting from the first step, I'm just multiplying those propensities by 3/4 if it's in the training set and 1/4 if it's in the test set, because that's the propensity for seeing that rating in that data set, right? And now I can, while doing my cross-validation, I can look at propensity-weighted reconstruction error to pick my hyperparameters, right? And then for a good point for the propensity estimation, we were actually very aggressive with our logistic regression regularization. So we wanted to underfit rather than overfit, going by the theory that said that overestimation is good, underestimation is bad. So I wanted to like regularize the logistic regression heavily so that I don't get small propensities. But awesome questions. But I also want to now switch over to the second project in the remaining 30 minutes or so. So from the evaluation problem, where we talked a lot about biases and using propensities to fix those biases, I want to talk about the learning problem, okay? And then I chose this project because after talking a lot about biases, we are going to now talk a lot about variance. And for a machine learning talk, you want a bit of both bias and variance. So again, the one sentence summary for this one is, I want to take supervised learning algorithms like deep networks, SVMs, conditional random fields, and I want to have them train directly with logged banded data, okay? And I want to think about arbitrary structured prediction. So I want to do something like structured prediction, but using logged banded feedback, okay? One thing I do want to mention at a meta level is the evaluation question and the learning question are very nicely decoupled, but also interrelated in the sense that advances that we make in the evaluation question naturally dovetails into improvements in the learning problem.
What's the structured prediction here? What is this? What are you trying to predict?
We'll end up doing multi-label classification for in the experiments. So we are developing a general theory for structured prediction. You can drop in your favorite structured prediction algorithm, right? The model that you use is up to you. We'll be ending up using CRFs, but bit of foreshadowing, everything works fine for any deep net with a softmax layer on top. So yeah, but that's like the punchline. That'll come right at the end. Yeah, I also wanted to mention that counterfactual learning has been much less studied compared to supervised learning and online algorithms, things like explore, exploit, no regret bandit algorithms. This idea of like, can I take logged exploration data and do something, right? You can no longer guarantee no regret because it's conditional on how that exploration was done. But you can still answer, well, how best do you exploit, right? It's heavily understudied. That's a very bad way to say it, but it's not as much explored. That's a very bad one. Okay, so let's put some notation on the board. So I'm thinking of a system pi. Okay, pi is something that's responding with actions when in comes a context x, right? So it's getting you from x to y's. How good is pi? The evaluation question. I could have summarized all of it via just this risk, right? It's just expectation over the inputs to the system, expectation over actions taken by the system, what's the feedback like, what's the reward like, right? And the challenge when I was trying to reuse log data was that the data that I had actions coming from some other system, which I'll call pi naught, okay? So I want you to think of the controlled assignment mechanism setting here, right? So the only reason I'm having selection effects and biases and things like that is because pi naught was in control of taking actions in the past, and now I'm asking, well, how good is a new policy pi going to do, right? Without having to actually deploy pi and letting it take control of what actions to take. So in the assignment mechanism land, we are in the control setting. We know the propensities, so we just log them. We just log the propensity for taking some action under pi naught. Okay, bit more intuitions and definitions. So when I said pi, you might have thought a functional mapping going from x to y's, but without loss of generality, you can think about stochastic policies, like distributions over actions. So via a visualization, you can think about the space of all actions you can take as the square. Okay, a particular point there is an action that you can take. The color tells you how good that action is, right, as determined by delta. And a function is like, picking a point in this space. A distribution is basically defining this Gaussian or some cloud, and then you're sampling points from this space. Okay, so I gave a proof by authority that IPS is going to be unbiased if things were unconfounded. Well, in the control setting, it's very easy to see why IPS is unbiased. We have a logging policy, pi naught, that defines a distribution that way. We got to draw samples from this distribution. Those are these dots. And then you get to see the colors, right? The red and the greens. We have a new policy. That new policy is a different distribution, right? So I need to do something like importance sampling to fix the mismatch between these two distributions. And that's all that inverse propensity scoring is really doing. It's just treating all of this as Monte Carlo estimation. And it's just reweighting samples that you drew from one distribution to make the expectations match another. Okay? So it's basically, in this control setting, it's just domain adaptation or importance sampling that's going on. So the problem now is to find the best policy, pi star, in a policy class. Okay? So you can write that as this unachievable goal. Try to find this argmin over pi of the risk for that particular pi. Remember, R of pi is an expectation, but we can only ever work with some finite samples that we can draw from pi naught. Right? The workhorse of machine learning, standard machine learning, is empirical risk minimization, okay, which tries to do something like this. It tries to estimate r hat of pi on some training set, and then it has an additional regularizer to prevent overfitting to that training set and picks the minimizer amongst these. Very high level, you can think about these regularizers as arising because of the variance, and by reasoning about the variance in the mean estimates of a finite sample estimator. You can also think about this regularizer as being needed because, hey, you're using the same set of samples to test a whole bunch of different pi's. So you need some additional thing to prevent to correct for multiple hypothesis testing, right? I don't think I need to give these intuitions to this audience, but still. We might think that with IPS, we have already solved the problem because ERM and IPS are a natural fit. I can use IPS estimated risk, right? So I have my logged bandit feedback. I would replace r hat of pi with this IPS weighted estimate, and things will work fine. Remember, I showed you a picture like that, right? It's an unbiased estimate for how good this new pi is doing. The trouble is that's not all that's going on. We are now doing an argmin over all pi's. In particular, even for moderately rich policy classes, it's very likely that you have a policy that behaves like this, right? You have a logging distribution, and the new policy is way out in the ethers, right? If we try to do importance sampling in a situation like this, every importance sampling diagnostic that we construct will tell us that importance sampling has failed, right? Either collect more samples or change your sampling distribution so it's more supported in the regions that pi prime wants to pick, right? So the diagnostics will tell us importance sampling has failed. Can we use those diagnostics? Can we detect and avoid IPS failure while we are doing this learning? Rather than first doing this argument, almost always picking something like this and then realizing, oh, we failed, okay? So,
Like as a trade-off, like you decide like how close to beta optimal or versus like how confident you are that in the power.
so the intuition is absolutely spot on. Well, you can think about this as a proximal update in policy space, right? Like I know if I drift too far from the logging policy, then my estimates become too uncertain, and so don't go too far. Or go only as far as you're very confident that the gains are worth the step, in some sense, right? And that's what it's going to boil down to. And it's actually an open, like after this, I'll come back to it though, the proximal update view of the whole problem, right? But let's actually revisit the issue of the regularizer, right? Like why did that arise? So in classic ERM, we had a training loss and a regularizer, and that's arising basically from a very classic generalization error bound, a risk bound that Vapnik and Chervonenkis has proved. That's an Easter egg there. Can anyone recognize the citation?
20,000?
No. Like usually you might see Vapnik's papers from the 80s being cited, right?
Oh, wait. That's earlier.
That's earlier.
Oh, I see.
I found a German copy in Thorsten's office. So Thorsten had a
Something like on the uniform convergence of set values.
Really? Oh, that's
Yeah.
earlier.
a German translation. Anyways, so these guys proved this amazing bound on the true risk, right? So you can upper bound the true risk with the empirical risk plus something that tells you the capacity of your hypothesis class. So this is the structural risk minimization principle. So and then this is arising basically via a Hovding bound argument and then taking just a union bound over the entire policy class. But the key point here is in supervised learning, you collect a set of data and the choice of your policy does not affect how much data you have collected, right? You have n samples, you're testing all these different policies on the same set of samples. When we are using importance sampling to get an unbiased estimate, the effective number of samples you have collected changes as you pick your policy. So if you pick something that's very similar to the logging policy, well, you have how many ever logs you collected. If you pick something that's way out there, the inverse propensity weight for that guy, the importance weight, is so large that it just drowns out all these other samples. So it's as though you have an effective sample size of just one. Okay? So the size of the sample on which you're evaluating your r hat of pi depends on the choice of pi here, right? So we want to revisit those risk bounds and actually reason about this additional variance. So we used Maurer and Pontel's empirical Bernstein bounds to come up with this more informed risk bound, right? It's going to have a very similar shape. It's going to have the off-policy estimate of the risk. It's going to have a capacity regularizer, but it has this additional empirical variance term, right? And this empirical variance we'll be able to measure during our training in some sense. And this has a very nice property that if your new policy is very close to pi naught, this empirical variance term is small. Okay? If this new policy is very far away, the empirical variance is very large. Those importance weights are much, much farther away from 1, and you end up having a very large empirical variance. So this naturally motivates the analog of structural risk minimization to ERM to the counterfactual risk minimization principle, where we just have this additional empirical variance regularizer, right? So this has this nice property of penalizing policies that are moving too far away. So getting back to the proximal update, you can think about this empirical variance as telling you how to measure these distances between policies.
So the risk bound part, so off policy one is that you know
The IPS weighted estimate.
is the standard way without taking into account online kind of interaction. Is that the way you meant by off policy?
No. I meant, so we had the bandit feedback data that we collected from pi naught, right? And now for every pi that I'm picking, I'll be doing this IPS reweighting, right? To make that data, to answer the question, well, how good would pi have done by looking at the data collected from pi naught, right? And the trouble was it was bandit feedback. So I used IPS to fix that mismatch, right? That is that off-policy estimate is that IPS weighting estimate. The trouble is this fix introduces non-uniform variance. If your new policy is close to the old one, this fix gives you a pretty good estimate. If the new policy is much further away, then yes, you have fixed the bias, but on a finite sample, the variance is now much, much larger, right?
Okay.
It's as if like, right? So that's the second term that's basically governing that. So essentially what we have done is during this training, we are directly accounting for this variability of these importance weights as we are searching through the space of policies. Okay.
So what do you call it? Counterfactual? In what sense?
So empirical risk was basically saying,
What you had before.
yeah. So it's just a cute play on words, nothing more. So
So I'm just going to get.
yeah. So what did Vapnik do, right? Vapnik said, I wanted to minimize the true risk. Right? Instead, I'm going to minimize an empirical risk estimate. How do I do that? I'll just sum over my training data set and take the average of the training error, right? So this is a standard empirical risk estimate that I'm minimizing, right? Here, it's not a standard average through your training set and minimizing something. We needed a counterfactual estimate of how good a policy is, right? It's again, you can think of it as just another empirical estimate. It's another Monte Carlo estimate.
That regularization at the end is the same as the one in Vapnik.
Yeah,
Right.
the capacity control is this.
Counterfactual is just adding that variance term.
Exactly.
Okay,
Right.
okay, I got it.
Yeah, and then the whole point is like the constants will differ between these two risk bounds, right? The way they decay differ, but anyway, we just like even in structural risk minimization, we have a very complicated like covering number based argument that gives us a capacity. We just throw all of that out, put one regularization constant that we pick via cross validation, right? So here we are anyway doing the same thing. So those additional constants in the bound don't matter.
So rather than treating these two as parameters,
So yeah, we are going to be treating lambda 1 and lambda 2 as hyperparameters.
the method will be different than the one without taking into account the counterfactual.
Exactly. So if I didn't have this term, we might end up picking a different lambda 2.
But in practice, do you do line search to get lambda 1, lambda 2? Yeah.
We do a grid parameter and do cross validation to pick it. Yeah, exactly. So yeah, you can think about it as I've just introduced one additional hyperparameter.
Just a very minor comment. So actually, you can just simply remove square root, right? You don't need the square root. In the middle term.
I don't need
You
the
just
square root in which one?
For the middle term.
The
You
middle
just
term.
need the lambda times variance of a pi.
When you may want to make it into the same on the same scale.
But even for the regularization, for the last term, if you consider the regularization part, it's also square root of this dimension, or square root of W2 norm, right? But you don't need a square root of W2 norm in the SYM.
So what's the
What do you mean you
theory?
don't need?
So what's the theory? I remember reading Toby's
So if
paper.
you
There was
are
a lot of
If you use
justification
the
about that.
necessary, so that means the bar will be square root of
Yeah.
W2 norm, right?
So the question is that what is the cause
It's also
of the square root?
of this dimension.
Oh, what is the cause of this square root?
Square root, yeah. So you probably.
Oh, that's basically because we are just using basically Bennett's inequality. So rather than using Hoeffding, right? If you were to use Hoeffding, you would get like a square root 2 log some 1 over delta by, okay, if I wanted to say something like with probability at least 1 minus delta, I want to guarantee this bound holds, right? I would have something like square root log 1 over delta times the range of the random variable times a covering number sort of thing in the classic bound, right? Here what happens is rather than using Hoeffding, we want to use Bennett first, okay? If you want to do a Bennett inequality, you will end up having square root log 1 over delta times the true variance of this random variable, okay? Plus log 1 over delta times the range of the random variable, okay? Times the covering number. So the whole point of Maurer and Pontel's work was to say how can I get from something that's not measurable, right? The true variance of this random variable to something that I can measure, which is the empirical variance of this random variable, okay? So that's what they do, and they basically do it by reintroducing a whole bunch of additional constants. They'll end up having like crazy constants showing up in the first thing, but the square root n infinity, so in the second term, you will have the covering number show up outside the bound. In this one, the covering number shows up inside the square root. Like there'll be two terms in this bound. So it's basically like this term decays as 1 over square root n, this term decays as 1 over n. So this one is a much faster decaying thing as you collect a number of samples.
I think for that reason, maybe square root should be there.
Yeah.
So I think,
Yeah.
Otherwise.
Because this thing decays as 1 over square root n, like even in the overall bound, even before we start throwing things out and putting like just lambda ones, right? So you still want to ensure that this is dominating this other term. But honestly, very, very honestly, we looked at the Vapnik paper, and there is this leap, right, from the risk bound where you just replace the, from the covering numbers, you eventually go like the VC bound is now upper bounded by like square root norm, right? And so let's replace that in there. So there's a pretty loose bounding argument to finally come with this, right? And we were essentially like, okay, let's just throw all those constants on to just plug this additional constant in, because that's the sort of dirty thing we are doing anyway for SRM. So there is work to be done. So my point is, this is a first step. Cite me when you build on it and make it better.
It also makes it
It's
harder
not-
to
No, I think this whole discussion, jumping into the technical details of Bennett and so on, that's not the reason. Look, you expect this second term to change like the standard deviation, not like the
Yeah.
variance. There's no reason why it should be the standard deviation squared, right? You expect it to behave
I mean,
linearly.
like even this term is the standard deviation.
Right, they have this linear effect. I mean, the square root will be there even if you use something not Bennett. Bennett is just a technical thing. We should not
Okay.
jump into those details, right? You look at a bound like this, you would expect it to change like the standard deviation, right? Like square root of variance. There's no reason why it should be quadratic.
I mean, even the original Vapnik bound, that capacity control term, is the standard deviation of the risk estimate that you write up there. Right? That whole covering number argument, that's
But
the
you
standard
don't know
deviation.
how tight the bound is.
It's not tight. Oh, it's definitely not tight.
This is a principle thing. Okay.
No arguments there.
But the
Again,
square
like
root makes
inspire.
it-
Huh?
The square root makes it harder to optimize.
Haha. Next slide. The slide after this. We have tricks for that. But thanks, that's a good compliment. So we implemented this. I'm showing you the structural SVM, just a linear model, right? You have a feature vector for every action that you could take. And you're just trying to get a score, a linear score for that feature action, and you're just defining a Boltzmann distribution over all the actions you could take. So this is the form that structural SVMs or CRFs basically are modeling. And so the goal of the learning problem becomes to take these X, Y, delta, and P. P are the propensities for the logging policy to take an action, right? To come up with a good weight vector, W. But just at a glance, you should be able to see that this exact same thing works for any deep neural network with a softmax output layer, right? Because they also define a Boltzmann distribution this way. As a foreshadowing, we'll be solving all of this via stochastic backpropagations. And then the current work I'm doing that's getting prepared for submission is exactly, hey, by the way, POEM works awesomely with deep neural nets. Dropouts, AdaGrad, RMS prop, everything nicely fits together. But let's instantiate it for structured prediction because I'll have experimental results to talk about this. So the CRM objective becomes something like that, right? So if that's your output layer's probability for picking an action, just multiply the probability times the reward, but reweighted by the propensities. So that's that off-policy estimate. But then we had to additionally reason about the variance. So don't just sum over these things and take an average. You additionally want to take the standard deviation of that term and then have a regularizer on the W, right? Now, you're absolutely right. The square root looks annoying to optimize. And oh my God, I have to optimize this via a batch method. This objective is not convex in W. Even if I drop all these other terms out, this objective is not convex in W, which is kind of the reason why people used log concave distributions when we were doing CRFs, right? Because that gave you a convex objective. But for something like risk like this off-policy estimate of risk, that's not convex. So we want to use stochastic gradient descent to optimize this. And so we have tricks.
Doesn't matter square root or other.
No, so essentially how do you optimize this via stochastic gradient descent, right? It's not clear. So what we end up doing is majorization minimization. So we have a square root looks like that, right? You can take a Taylor approximation to square root at any point.
It's gradient descent, right? I mean, take a derivative of the square root, otherwise the gradient is, its closed form is there. Right?
But
As long as the
so-
gradient closed form is there, then you apply all the deep learning tricks to optimize.
It doesn't have to be compressed.
Yeah, it doesn't have to be convex. That's not the
Yeah,
issue.
exactly.
The issue is I want a way to be able to sample one data point from this and argue that the expected gradient I compute is indeed the true gradient of this variance, right?
Because that objective function itself contains sampling.
Exactly,
Okay,
right?
I see.
Right?
That's the
You-
difference.
yeah. So how do I now optimize this by stochastic gradient, right? I need to guarantee that whatever gradient computation I come up with, the expected gradient of that is the gradient of this, right? And to do that, we do this sort of upper bounding argument. So you can take a Taylor approximation around the current W that gives you a fine upper bound, and a Taylor approximation basically just gives you like some of these squares, some of this, the whole squared, and you're essentially just having additional constants floating around that you can now optimize this by sampling one particular I index from your data set, compute the gradient of Q, compute the gradient of Q squared, and then multiply these constants in. So it's like every epoch I just update these constants. It's like a iterative majorization algorithm, a majorization minimization algorithm. Yeah. So all of this is implemented for CRFs and linear rules in code up there, but the bit of foreshadowing is all of this works really well with deep neural nets too. So we have played with AlexNet on ImageNet, so logged bandit training of AlexNet works, training dense nets on CIFAR 10, CIFAR 100, SVHN works, MNIST with just a classic, the Patrice's.
For those nets, you don't need to do all the sampling as the way you are doing it. I think this is probably the question of the problem.
No. So if I wanted to train those nets not with supervised ImageNet but with bandit feedback data,
Oh, I see. Okay, so
how can I do it, right? So we have we haven't yet published it, so I don't want to give strong numbers to it, and we are right now running.
Image stuff. How did you formulate the feedback from there?
Good question. So
Security. That's something I think pretty crucial.
right. Okay. So ImageNet, you have an image and you have a bunch of categories annotated with it. Instead, imagine image. The current AlexNet is just predicting some categories for it, and the Turker is just saying, does this look roughly right or not? So the Turker is never telling us, is it actually the correct category, right? The Turker is never telling us all the correct categories for this object, right? Because also label noise for things like subspecies of dogs and subspecies of birds is very high, right?
Okay.
What you instead want from the Turkers is just you show this image, you show the category that's being predicted, and then the Turker says, is it roughly right or not, right?
Pretending that crowdsourcing, information is feedback.
Yeah,
In a way.
exactly. So I don't have to additionally get like all the correct categories for this.
This kind of thinking would be very, very useful for this newer brand, direction for this adversarial network.
Exactly.
So
right?
did you look into
So,
the literature?
not yet. Not yet.
Yesterday, there was Stanford has this whole 2 days of learning school. I was listening to them. It's a big topic there, so I think it will be a huge amount of contribution for that.
Yeah.
And this kind of bandit feedbacks are easier to collect than supervised learning feedback. For example, in QA, your search engine can answer the question and the user may like or dislike the result. But the user doesn't have to provide the actual answer to the question.
Yeah, okay.
So it's much easier to
So
collect.
the application related now to the quality of the crowdsourcing label.
Yeah. But on the other hand, you can use users to collect the label.
That's right.
That's the
That's good.
feedback.
The current election shows us, though, that user consensus and the truth can diverge.
I see. Okay.
To bring the discussion back
Okay.
and let us move forward, we'll come back, we'll revisit this, right? Like these are good ways to build on this, right? So I like to brag about this. So in a big media company, they actually tried to use Poem for their vertical placement algorithm. It's not Google that I'm talking about, another media company. They wanted to figure out like in comes the context, which is a query and a user, and the SERP looks like this. I have a news box. Do I place it in this position or that one or that one or that one and so on? So they had like 8 different positions that they could place things in. And the loss that they defined is the mean reciprocal rank of clicks on the entire SERP. And they cared about that because just by placing this in the first position, it can get a very good click-through rate, but it can cannibalize clicks away from the rest of the page. So they still wanted a good overall search experience. Okay. The logging policy. So they had a pretty what they thought was a pretty good production scorer that would score all these different positions and pick the largest score to place it. And so you can just use those scores to define this multinomial distribution to do exploration, right? So the logging policy is just a multinomial defined using those scores, and that gives you a way to explore placing this in different positions. but this is exploration guided by the current production ranker. So on the left, I'm showing you the production scoring algorithm's performance. It's losses, so lower is better. So these are averaged over 100 different data sets. So we had like 100 different instances of these logged bandits collected across 100 different days. And we are reporting, well, how good was the rule-based system then? And each column here is actually reporting one of those instances. And POEM is basically, well, I take that log data and I use it to train this linear weight vector, right? Using the features for the context and the users and the ranked documents and so on. I'm trying to learn a weight vector. And I'm now asking on like a whole held out set of those impressions, how good is POEM doing after you have learned this weight vector, right? So that's what that performance is. And you might be worried by the variance, but honestly what's happening is so 100% is basically relative to the production ranker. So if you saw a bar at 100, that means it's as good as the production ranker. Anything lower means it's better. So 50% means it's like twice better than, it's like a 50% reduction in error rate compared to the production ranker, right? So across these different repetitions, POEM is almost always better. And the big variance that you're seeing there is actually just coming from this inverse propensity scoring to help get an unbiased estimate of its performance. So it's the fact that the new policy that POEM has learned is actually a bit different from the logging policy, and that's causing some additional variance. If you actually deploy it, it's just almost always better. Okay?
Is it public data or?
No, they do not want this to become public data. So this is not the company that you're thinking of. It's a different company. So, okay, I did want to spend at least 5 minutes talking about future steps too. So I spoke about how we can reuse this data to help evaluate and train models, and I gave ideas about IPS and POEM as a way to do this additional variance regularization. So these two projects actually illustrate two different approaches to counterfactual analysis, and they also tell you that these approaches are not mutually exclusive. So one way you can take when you're faced with this incomplete information problem is to just try to model the world, right? Which is what we were trying to do in the Netflix challenge, right? We got to see only a subset of user item ratings, but with that we wanted to model how would a user rate every other movie in the inventory, right? Like predict what a user would do for every possible treatment I could assign him to. Because if I can do that, then I can derive a recommendation policy easily, right? Like if I knew what a user's predicted rating for any movie would be, I can just give him movies that they haven't seen that we predict they would like, and we are done. We have solved the whole recommendation problem, right? On the other hand, POEM was directly trying to get at a policy that's going to give good aggregate CTR or good aggregate revenue or a good aggregate online metric. So it cannot tell you what the user's preference for an unseen movie will be. For example, POEM is only dealing with aggregate estimates, and it's using Monte Carlo estimation to do it, right? But these projects also tell you that these two approaches are not mutually exclusive, because in the MNAR project, we worried a lot about the biases that go into the data that we actually get to see. So even though I was in the business of trying to predict what a user is going to do for every possible treatment, I still needed to reason about the biases that go into the training data there, okay? So call out to some of the other projects that I've done. So the POEM, the counterfactual risk minimization stuff, actually raises a fundamentally new kind of bias variance trade-off in these logged bandit feedback problems. So it's quite fascinating, and it's quite unclear what's the best way to solve it, okay? So it turns out that we are now vulnerable to a new form of overfitting, where we are now overfitting to the propensities as opposed to just overfitting to a finite training set or the losses. And it's not obvious to me yet that just statistical properties like bias and variance tell us the full story here. What we ended up doing was to take a self-normalized estimator, which has slightly worse statistical properties, but it has very good optimization properties, because the fact is, after we build these off-policy estimates, we plug them into an optimization algorithm and search over the space of all policies to find the best one, right? So we also want good optimization performance. And the self-normalized one, by being equivariant, actually ended up not doing propensity overfitting. I think that's like just making me think, like, what are other such optimization-inspired guarantees that we can come up with, and then we have a toolbox of variance reduction techniques, and what's the best way to use all of them, and how do they all interact with each other. In work with the MSR New York lab, we looked at how we can extend IPS-like techniques to combinatorial action spaces, things like trying to solve search as a combinatorial contextual bandit, right? So the trouble is IPS does not exploit the structure in the action space at all, but we know rankings have a lot of structure. Can we exploit that, right? So the Slate's estimator ends up being this nice intermediate between IPS, which is very general but has very high variance, and making some parametric assumptions about the reward, saying that the revenue is linearly related to the things that I showed the users and things like that. Oh, this was a nice one. So this is under submission, but it's also up on archive already. So we might be worried that all I talked about today was sort of conditional on a logged exploration data set, and for things like ranking, if we have to explore the space of all possible rankings, we'll be host, right? Here, we sort of weaken the sort of guarantees we want from our algorithms, and I'm instead going to piggyback on users' randomization. So this is again inspired, it's a natural combination of POEM and MNAR. In MNAR, like users browsed through an inventory of items and gave me ratings, and I estimated propensities and did something. In POEM, like the system showed actions, and I used inverse propensities to do off-policy learning. Here, I bring both together to do learning to rank just by using clicks, okay? And this is not the way LambdaMart does it, or by having like click-based tweaks to the thing, but to actually think about what's the counterfactual nature of this problem. And it turns out that I can repurpose like classic click models that we have used, that we have done over a decade. We can repurpose them as that propensity estimation step in the MNAR project. And that ends up giving you a very, very easy way to incorporate users' click behavior, which are biased, have very simple click models, not the full-blown generative models that we typically do, and then use a discriminative algorithm that directly optimizes for the loss function of interest, right? Things like overall click-through rates and things like that. And then all of this Monte Carlo estimation work I talked about is not restricted to just estimating online metrics or interactive metrics offline. You can redo the same sort of thinking for designing offline data sets. Like if I have to collect a bunch of judgments from my Turkers, what's the most efficient way to collect these judgments, right? I can redo the same Monte Carlo estimation machinery and come up with optimal ways to sample documents that get judged for an TREC collection in information retrieval. Looking ahead, I think causality, causal inference, and machine learning are naturally allied to each other, and we are barely scratching the surface. Inverse propensity scoring is from the 80s. We have like 3 decades worth of advances in causal inference that we can bring to bear on these problems that now arise because we have become too successful in predicting things with machine learning that we have started embedding them in actual interventions with the real world, right? So the moment machine learning systems are intervening with the real world, we better start reasoning about the causal effects that underlie all of this. And then we are starting to see advances, like the stuff that I talked about today, but also I'm a fan of the Causal Bandits paper that's going to come out in NIPS now, right? Do check it out. It's a very, very good first step to also improve online explore-exploit algorithms and give better regret guarantees the way we typically study by additionally thinking about causal models. Causal Bandits. Latimore et al. And I really think that these causal models give you a very nice abstraction to answer the question how to explore. Right now, I like online algorithms and regret minimization as a good way to think about good exploration strategies versus bad ones. Things like, epsilon greedy has worse regret rates than, optimism in the face of uncertainty. Those are good, right? But they are necessary. They are not sufficient. We need ways to cleverly explore very large spaces. And the fact is, just generative modeling is not the answer because the agent always has the ability to intervene in the world to efficiently build these other abstraction models too. And I think causal models are the right abstraction to tackle that. Overall, I like to think of this general reinforcement learning picture. I know that I need an off-policy algorithm to be able to take all the data that I have seen ever and be able to exploit it correctly. I also know that I need causal reasoning to have a good forward model for the world, right? And so, I mean, I just chose an actor critic thing because it was the first thing that came up on Bing images search, okay? But you can think about any model-based RL system, right? And I need off-policy algorithms. I need a way to build those models and to get a good reinforcement learning agent. But with that, I'll conclude, and we have 15 minutes for questions.
Yeah, we have time for one or two quick questions.
I think it was slide 32. Go back. Yeah, so in this, you had mentioned the distance from the current policy, and it's not obvious looking at the empirical variance how that measures distance from the current policy in any way.
Very nice question, right? So it's implicit, right? So that's what I meant by, so the proximal update is a very nice intuition for going after this. Like, here is one way to think about the whole problem, right? To make this proximal update thing more concrete. Like, okay, how do I want to measure this distance between policies to say that I don't want to go too far from where I have data to support my conclusions? And we can do the whole like natural gradient kind of argument, right? We could say that distances in parameter space doesn't make sense, right? Because you could just reparameterize the space of policies, and that would give you a very different notion of distance, right? What we typically see in off-policy reinforcement learning is a consequence of natural gradient. We say, look at the distribution over actions implied by one policy than the other, and minimize something like the KL divergence between the distances, between these two distributions, right? And so that's like an explicit regularizer on like not having an action distribution that's very different from the one that generated the log data, right? So that's an explicit distance, and I think Peter Abil had a paper in ICML a year or two ago going after this, right? The reason I don't find that satisfying either is think about a situation where you have two good actions and a whole host of crummy actions, okay? And imagine a logging policy and a new policy that plays the same probability on the good actions and have very different distributions over all the crummy actions, right? In terms of the returns of deploying these policies, changing from one to the other doesn't change much, right? But in terms of distribution distance, it's a lot, right? So I know that the proximal regularizer that I want will additionally reason about the rewards for picking actions in particular things, okay? The empirical variance has the reward, right, the delta. It also has like a weight here that's telling you how far it is. But as a consequence of being an empirical variance, you're only measuring it at the actions that were chosen, right? Not the entire distribution of all actions you could take, right? So if I was in a situation where I know the full logging policy distribution and I know the full new policy distribution, can I actually explicitly come up with a distance that is risk sensitive, right? It's not risk agnostic, but actually formalizes this proximal update and gives you guarantees, right? I don't know, but I think it's there. It's somewhat intermediate between empirical variance. Like the only reason I don't like this is because it's not it's confounding two different sources of uncertainty, right? Like rewards for actions not taken versus my importance weights for actions not taken. One of them I know completely, right? The importance weights I know completely in some situations. So I should be able to like sort of decouple it and get a better regularizer here, right? To do, but it's got the spirit of like the importance weights there has the spirit of distances. Like the further away you are, that has much larger variance. The rewards are the one that prohibit like directly thinking about this as distance in policy space, right? It's like a risk-weighted distance, which is.
I mean, you gave a different motivation for it originally, which was the effective sample size, and it'd be interesting whether or not you could think of just the deviation from uniformity on the inverse propensity weights as being a measure of the variance that you're talking about as well.
So that's exactly what we do in self-normalization. So the thing that you normalize by is the effective sample size as opposed to the number of samples you actually collected. That's exactly that, right? But it opens up this next question, right? Which is, okay, we used this to come up with a self-normalized estimator, but is that the best we can do, right? Because now we know there are at least two different ways to control this variance term, right? You could also have explicit variance controls. You could also overestimate those propensities that are too small and underestimate the ones that are big, et cetera, right? You can do a bunch of different ways to control the variance here, right? Like at this point, I know that the variance is important to look at. I don't yet know what's the best way to control them all. right? And we have many different in the toolbox. And I don't want to stop the story at, hey, just try them all and see which one works best, right? Yeah.
One quick one. Can you go back to the same slide for each second? So here, how difficult is it to change this? So later on, you talk about the particular model, linear model. Here, how easy is it to change that to a general nonlinear model?
So anything that has a Boltzmann-like structure just works, right? Straight out of the box. Like the Taylor approximation, all the stuff that we do to handle the variance term naturally fits with anything that's like a Boltzmann distribution, right? So
as long as the network has a soft.
So exactly. So softmax layer on top already done. Right? It's already taken care of. Like don't do that because I'm submitting something there. Okay, don't scoop me. But for anything other than that, like for for general, I mean we have a whole bunch of other loss functions up there too, right? We have other output layers there too. It's to do. Similarly, ensembles of random forests, I'd like to be able to do this for decision boosted regression trees too, because they are so ubiquitous in a bunch of search applications. It's not trivial, is the way to put it. There are ideas to approximate like this variance sort of reasoning, but I haven't yet seen something that's compelling, elegant in theory, and also works great in practice. It's also hampered by the fact that sitting in academia, I don't have awesome amount of bandit search impression data.
Okay, so I guess if we have more questions, we can take it offline.
Okay.
Yeah. All right, thanks.
Thank you.